I'm feeling like if you weren't born, you wouldn't be here.
No, different thing. Okay. Here, watch this. Ready? Okay. Hope I don't break the window over there. Okay. Ready? Okay. So not like shocking, right? So it's just a thing swinging around. Lindsay, watching this? Okay. So the question is, what is keeping it in this path? What, from the block's perspective, if you're this guy, what are you going to say if I ask you, what is keeping you traveling in this circular path? The string, the tension in the string. Okay. Now take like a freeze frame of that. It's moving around in a circle. Just pause it somewhere. What direction does the tension point?
Always towards you.
It points along the string, right? So what direction? If you ask this guy, I mean, there's gravity here, which complicates things. You can probably see it's kind of pulling on my hand as I swing it around. It's a little heavy, but this would still work. If I was an astronaut out in a zero-G environment, right, I could still do this. But the key idea here is a very central idea is, if you ask this guy, what direction is the force exerted on you? He's going to say along the string. So towards, that vector would point towards the center of the circle that it's traveling. So that's just the first thing you got to really like wrap your head around. Okay, so first little thought experiment here would be, look at problem one. Also, I mean, luckily this is an upper level class, so you've all driven cars, right?
Yep.
If not, you've been in a car. So you guys know that. So for number one, let's say you're driving your car. I'm gonna add the little straight parts. So this car is gonna make a left-hand turn, or I guess he's making a right-hand turn. Sorry, he starts at A. Here's A. So this is an overhead view of the car. So I don't know. There's the hood. There's the trunk. Okay, so it says, so what is the force exerted on the car by the road at these points? So from an overhead view. Okay. So if the car is traveling at a constant speed of 30 meters per second, first of all, what's the net force on the car if it's traveling at a constant speed? Net zero. Very good. Net force. And actually, I need to start qualifying that statement. What I should have said is, he's traveling in a straight line, so he has a constant velocity. There's a subtle difference there. Okay. So now there is, of course, there's a force vector pointing into the board. What's that called? The vector that points, yeah, it's called gravity. So gravity points into the board, normal force points out, but that's not really what we're concerned with right now. What we're concerned with is the fact that as far as going forward, backward, left and right, from his perspective, the road doesn't need to exert any force on him in order to keep him traveling in a straight line, okay? But as he travels through this bend, okay, let's say there was no friction. Let's say the road is really icy. What's the car gonna do? Yeah, he's gonna slide off the road. That's a big idea in this. Believe it or not, it's actually something that's a source of a lot of confusion. A lot of people have trouble wrapping their heads around this idea that that the road is going to exert a force inward. Okay, the net force is going to point inward, because without that force, again, if there was ice on the road, a lot of ice, so there's no friction. Well, the car is traveling this direction, so he wants to just slide off the road. What's the only thing keeping him in this path is a friction force exerted by the road that pushes him towards the, there's a dot there, that's the center of the circle. So this is a little circular arc here. Does that make sense? So when the car is here at point B, the net force vector points inward. Okay? We're going to calculate the size of that vector in a minute. Now, once he's out of that bend, how about now? Where's the net force now? Zero. Now, of course, if on the straight part, if he wants to speed up or slow down, right, the net force would point this way if he's speeding up. It would point this way if he's slowing down. But it says he's maintaining his speed the entire time. So, okay. Now this raises a very big question, which is you go, well, say, wait a second. I thought you could only have a net force if there was a change in speed. If you're dealing in one direction, that's true. But with 2 dimensions, technically the rule is the net force is, here, let's show a little bit of notation here. So net force is mass times acceleration. So mass times change in velocity over time. So all you need is a change in velocity, not necessarily a change in speed. Okay, so if I'm traveling, say, in this problem, if I'm traveling 30 meters per second in this direction, and then a moment later I'm traveling 30 meters per second in that direction, well, I change my vector, right? Velocity is a vector. So if you change the direction of your velocity vector, there must have been a force to cause that. There was an acceleration. So
this might be like slightly off topic, but like for saying this corner was like a lot sharper, would there also be like some sort of like, is it like friction directly from the road to the car, like making it slow down at all? Is that like, or is that just like higher level?
Making the car slow down?
Yeah, like.
I think what you'll find is, I mean, I would say no. Yeah. I'd say if you enter a turn, suppose you're in like a race car and you enter a turn at a high speed, as long as the road can provide sufficient force, friction force, that will be like high quality tires and in a high quality like tarmac or asphalt or whatever. As long as you can generate enough force to keep you in this path, then you should be good. You won't slide off the road. But the road's not going to slow you down. Okay. Now, are any race car enthusiasts in here? Anyone like professional race carring, like F1 or something?
They're called racists.
Very, very clever. Where do you hit the brakes? If you ever played a racing video game, you know this. Before the turn, yes.
And then you accelerate
through the apex. If you ever played like Gran Turismo or like Forza Motorsport or something, yes. And they show you these little guided lines. You want to hit the brakes like here, or same thing with mountain biking too, like or a lot of things. Like you want to hit the brakes so that you're pretty much like you're at the speed you want to take the turn at, like here, and then you take the turn at that speed. Now maybe if you're being really aggressive, you can start accelerating at the gas at the apex. But anyway, the idea is, and we're going to talk about why this is in greater detail, but you don't want to be hitting the brakes here because you are trying to get as much friction as you can to point you towards the center of the circle. You want as much of that friction keeping you in the circular path. You don't want that friction also trying to be slowing you down. Does that make sense? Because if you're trying to slow down, now that friction vector has to also point this way. You're asking more out of the friction. So you're not going to get as much. You're more likely to start skidding if you hit the brakes during the turn, which you guys may have experienced if you were driving too fast and hit a turn and you're like, oh no, I'm going too fast. And you hit the brakes and what?
I appreciate the glances towards me when you're making this reference.
Okay, I'll show you a little bit of mathematics here. It's a bit of a miraculous result too. It's an amazing result because you might go, wait a second, we got to start now doing two-dimensional vector stuff to analyze this system, right? Because I got a vector pointing in the x direction, and then I got a vector pointing in the x and y direction. So that's going to complicate things greatly. Actually, the way it turns out, I'll show you here for this one. So look at this arc. Here's the idea. So this is a circular arc. So what I'm showing you here, just to make full disclosure, I'm showing you where there's a famous formula for how much acceleration, like what's the acceleration if you're traveling in a circular path like this? How do you quantify it? I'm going to show you where that comes from. Okay. So one moment in time, let's say my car is here. Here's my car. I'm traveling through this circular arc. Okay. And I've got a velocity vector. Okay. Call this like V1. Now, a moment later, I will have traveled some distance along the arc. Okay. I would have traveled some angle theta. And now where's my velocity vector point? You guys remember the fancy vocabulary word for how to describe the direction of these vectors? Tangential. Very good. These vectors are, you can flex your wrinkly brain knowledge on, right? It's not just the size anymore of the brain, it's the wrinkliness, how much wrinkles. You don't want to be smooth brain, right? Anyway, so these are both tangential. They're tangential to the circle, okay? Complicated drawing, right? Now, of course, this is the radius. Now, Enzo, you did mention something about the sharpness of the turn, which brings up a very interesting point. Does the radius of the circle matter? Yes, it's going to matter. Obviously, you know this, right? If you take a really tight turn, small radius, then that's different, right? Different experience than taking a very wide, big radius turn. So, cut to the chase here. So, these two vectors, so you've got vector 1, I'm going to draw them together like they're buddies, okay? I'm going to draw them together into a triangle. Okay. Now we didn't spend a ton of time on like vector analysis stuff, so you probably don't know this one. It's okay. This here, if you think about it, this is the difference between those vectors. So if my vector used to point this way, now it points this way. The change, the delta V, points in this direction. So this is the change in my velocity. Does that make some sense, or I don't know? So I hope it makes sense. Now the geometry of this would mean that this is how far I tilted. So this is also theta. It's the same angle. Okay. And what else do we know? What do we know about the size of V1 and V2? They're the same size. All that changed was the direction, right? All that changed was the direction because we're maintaining our speed through the turn. If you want to talk about speeding up through the turn, well, you can do that, but it's just much more complicated. So anyway, who remembers their geometry? If I think of this as a triangle as well, this is where you got to get a little hand wavy because you got to talk about assuming this is a very small angle. This distance here, this dashed line here, would be my velocity times time, that being like my speed. So for this problem, that would be like 30 meters per second. Does that make sense? Because that's how far you would travel. Technically, you're traveling along this arc, but what you do is it's called calculus. This isn't a calculus-based physics class, but in a calculus-based class, you make a bit more. It's the same argument, but you would call this d theta. But we're not going to. Just imagine theta is small enough that this arc is the same size. It's pretty much the same size as this like straight line. Technically, it's a limit. I guess you guys all know maybe limits by now.
Yeah.
If you're taking pre-calc or calculus, we talk about limits. Anyway, so sorry, I don't get too hung up on math. These are similar triangles. They're both isosceles triangles with the same angle, so they're similar. So I can write a proportion. The proportion would be something like, I don't know, this is to this as this is to this. So I'm going to write that. Delta V is to, now I just want to talk about the size of this vector. How big is this vector? It's V, okay? Equals this, VT, is to R. Don't worry, we're almost done. By the way, if you're super confused right now, it's okay. Once we have the formula, we can just use it. Solve this so you get change in velocity over time is equal to, what happens here? V times V. E squared, R is on bottom. Now, what's change in velocity divided by time? That's called acceleration. Okay, now, I said it was miraculous, right? Look at that. Come on. Look how complicated that was. And look how simple the formula ends up being. That's crazy. It's amazing.
Who came up with that?
Huh?
Who came up with that?
Alfred Eisenstein? I don't know. I have no idea. It's a good question.
Some guy with a big.
One guy with a lot of.
I don't know. This is a pretty straight. A lot of these results that are pretty straightforward like this, in terms of like the formula itself is simple. A lot of those results came up with them hundreds and hundreds of years ago. That's a good question. My guess would be Euler, but I bet you it's an ancient Greek guy. That's my guess. My guess will be some ancient Greek guy, maybe like I don't know. Who would that be? Could be Euclid, Pythagoras. I don't know. Let me look it up. Okay, so all right, what does that mean for us? What does that mean for us? Well, what that means for us is for this problem. Okay. Now, is this going to be an easy calculation? Yeah. Watch. Now, if I've confused you greatly, just look at that. Okay. You can think about this at maybe a lower level. Just, well, my teacher told me that there's this thing called centripetal force. It points towards the center of the circle, and there's a very famous, very, very famous formula for what the centripetal acceleration is. Okay, great. Okay, so right here, the force would be, the net force would be mass times acceleration. Well, wait a second. Isn't the acceleration just v squared over r? So now watch how easy the calculation is. So what's the mass for this problem? 1,000 kilograms. That's the car's mass. The velocity, the speed, was 30 meters per second. And the radius was 20 meters. Now, do y'all see how the smaller the radius, the bigger the force is going to be? Like if you make this number smaller, right, that makes the overall value bigger. If you make the velocity bigger, it makes the force bigger. No, but it's not linear, right? So if you double your speed through the turn, what does that do to the force required? It makes it greater by a factor of 4. Yeah, it's 4 times bigger. So if you double your radius, it cuts the force in half. If you double the velocity, it multiplies the force by 4. So what do you get? So you get 900. So 900,000, half of 900,000 is 450,000, I think. You should get here 400. Did I do that right?
Yes.
Newtons. Thanks, Taylor. I appreciate you. All right. So. What?
I plugged in again, and I got 45,000. No.
Oh, yeah, Taylor, you betrayed me. It's 20, not 2. Sorry. Thank you, Aiden. Just kidding, Taylor. I still appreciate you. Sorry, it's 45,000, not 450,000, because I was dividing by 2, not 20. Moral of the story: never do math. Yeah. Or anything. Never do anything. Okay.
Just sit there.
Just sit there. Right, Henry? If you ever think about doing something, just don't. Nip it in the bud. Yeah, nip it in the bud. Don't do it. Don't do it. Okay, let's look at 2. So, number 2 is really similar. It's an overhead view of, it's just this time it's a ball is attached to a string and it's traveling clockwise in a circular path along a frictionless floor at 3 meters per second. So again, this overhead view. All right, so how do you think we're going to calculate the tension in the string? So this ball is traveling in a.
Oh, that was really good.
Thanks, Julia. There's the ball. It's traveling clockwise. Okay, so what direction then? Because part B is asking us to label the ball's velocity and acceleration vectors. So what direction does the velocity vector point if it's traveling? Yes, very good. How do we feel about that? This is very important that you understand this idea. Okay. We sure we understand? Okay. Now, then what would happen if there could be a little mechanism in there, or maybe the string could just break. What if the string broke and released the ball at this exact moment? What direction would it go? In the direction of the velocity vector. Okay. Now, as this thing travels around the circle, the velocity vector changes with it. So the velocity vector is constantly changing direction. It's always tangential. It's always tangential. It's always tangential. Okay. But if we all of a sudden release it from the circle, it would just travel in this direction until it ran into something or had a force exerted on it in some way. We okay with that? So another example would be, let's say I'm in deep outer space, I'm out there floating, and I start swinging a ball around on a string like I did earlier with the little weight. Let's say I'm swinging it around in a circle. Okay, let's say it's, again, clockwise. And let's say right here, I release it. So it's going clockwise. What direction is the ball going to go if I release it right here? Like that. That's what it's going to do. It's going to fly off tangentially. Now, if we're living on Earth, and there's gravity, it's going to head off in this direction. And of course, it's going to take a parabolic path, but the idea is its initial velocity vector would point tangentially to the circle. Okay? Tangential, 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 tangential. Okay. Acceleration vector is, let's use another fancy word. It's not tangential, it's good try though. Okay. I'll give you a hint. It points along the radius of the circle, so we call it radical. No, radial. These words aren't like ultra important, but it certainly is more concise to say, oh, the acceleration vector points radially, or it's a radial vector, or it points in the radial direction, than to say it points towards the center of the circle. Anyway. This is the acceleration vector. And then how do I calculate the tension? Now this is an overhead view. So what's the relationship between the tension and the net force? Huh? They're the same, right? Do we feel okay about that? Are there any questions on that idea? Let me say it one more time. The net force and the tension are the same thing. They're the same vector, right? Because again, this is an overhead view. So yeah, is there gravity pointing down? Is there normal force pointing up? These cancel out, so we don't have to consider those, right? Those are, into the floor, out of the floor, okay. The only vector that's left is the vector that's causing this acceleration. So when I go F net equals ma, it always comes back to this, right? Oh, All right. F net equals ma. The net force in this problem is the tension in the string. The mass is the mass. And the acceleration is what? It's v squared over r. Because it's traveling in a circular path at constant speed. So my tension is, what's the mass here? 12 times v squared, so 3 squared divided by the radius, which was 0.6 meters. It's 3/5. So what do you get there? 15 times 12? Whatever that is. Huh?
180.
180? Sounds right to me. All right. Do we have any questions on this, guys? Anything at all? Any questions? Any questions? Okay.
Will it be the same thing?
Yeah, so when we study orbits, which will be later on in the class, you'll have, here's Earth, or it can be anything really, but let's say this is Earth. And let's say here's a satellite you want to launch.
It makes sense, right?
Yeah, I don't know, it looks like a barbell. Those are solar panels or something, I don't know. What you're going to talk about is how this thing wants to travel in a pretty much circular path, okay? And how there's a radius associated with that, and there's a velocity you need to have it traveling at, and you would basically you'd set up, you'd go back to this, you'd go F net equals ma, and what we'll derive is, now the thing here though is you're so far away from Earth that gravity actually is less. Your G value might be, I don't know, 8.2, not 9.8, it could be 7.3, who knows? Just depends on how far away you are. Spoiler alert, it's this. I mean, the gravitational force is this famous G number times you multiply the two masses of Earth and the satellite divided by the square of the radius. Anyway, so we'll take that and set it equal to centripetal force and get them to balance out and figure out how fast, like what's a balance of speed and orbital distance that actually makes it stable. Does that make sense?
Yeah.
Because you can have a satellite that's really high and kind of slow, or you can have one that's really low and faster. So,
Then you use the whole thing of like, because there's some satellites that just stay in the same geographical location all the way around Earth, and some that just go to space.
yeah, if you can, so what you'll do, by that time, we'll have a better handle on the math of like rotational stuff, talking about like radians and rotational like periods and stuff. And so what you do there is you set the period to 24 hours. So you say, what if you want your period? What if you want to take exactly 24 hours to make this orbit? Because then the point that you're over top of will be with you the whole time. And then you can, that's a problem we're going to do in this class. Basically, yeah, how, the question is, yeah, how fast and how high does the satellite have to be for that to work? I will direct your attention, last thing today. So, I don't know, on your own today, take 10 minutes, try to knock out 1 or 2 questions. If you feel like these are actually pretty quick questions. They don't take a long time to solve them. But I did want to point out number 8. It's a very interesting question. We'll do it tomorrow. But some food for thought. If you want to challenge yourself, it's a very interesting, in my opinion at least, thought experiment. It's how do you create artificial gravity? If you were in a big old spaceship in deep outer space and you wanted the astronauts in there to feel like this, more or less. They wanted them to be able to stand there and, run and whatever. How do you do that? Well, you can use some kind of crazy dark matter, quantum entanglement, energy field, science fiction stuff, or you just get a big old cylinder and spin it around. Okay, that's the easy way. There's a famous shot in Stanley Kubrick's 2001: A Space Odyssey that shows this. It's featured in a lot of science fiction movies and stuff. You can derive actually, this particular room has a 20-meter radius. So the question's asking, how quickly does a 20-meter radius, that's a big cylinder, right? 20 meters as the radius. So it's 40 meters wide. The question's asking, how fast does that thing have to be spinning around in order for this dude, Bob, to feel his normal Earth weight? Right, so you're going to say his acceleration value is g, is 9.8. And so you're going to be, basically you're coming towards this and going, well, if I want this to be 9.8, what is my v and have to be? What is the r is given, and then it's asking you to figure out what would be the rotational rate in rotations per minute. So you might get hung up on that possibly, but I feel confident you guys can figure out that part.
So try to number 8.
Yeah, try it. If you get stuck, it's not the end of the world. But I was saying more importantly, maybe try to do 3, 4, 5, and 6. If anyone's like super stuck on those, we can certainly look at them in class, but they really are they just come back to this using this formula. So, okay, that's it for today.